Hi everyone, so welcome back to the videos. We are going to be doing another optimization question, this time using surface area, technically area and perimeter. Okay, so we are given a chapel window consisting of 4 equal rectangles, okay, and a semicircle. The length of the metal that has been used for the frame is 36. So these lines, all here, give us a value of 36, okay. That's just a bit messy though, so I'm going to erase all this. Okay, so one thing that I should say, for future, this radii, okay, I'm not going to refer to it as r from this point. I'm going to refer to it as x, okay, just because it's the same length as this over here. Okay, cool. So in question 1.1, we're asked to prove that the area for the frame is given by that a value, right? So first we're going to look at what the value of our area is actually. Okay, so we've got the 4 rectangles. So 4 times length times breadth. The length in this case is going to be h, and the breadth x, right? So that's how I'm going to leave it. Okay, hx. Then the area of the semicircle is going to be equal to half of pi r squared, which in this case is just x squared. Okay. Then what you can see, the difference between their formula and our formula for the main part, obviously they're different formulas, which would give you the same value, but different formulas. The h is not present in their formula anyway. So we know that we're going to need to remove h. So the way we're going to remove h is we're going to get h in terms of x and x values and normal values, right? Like numbers and like pi and stuff. So the way we're going to do that is we're going to work with the information they gave us. So they give us essentially the perimeter. So our perimeter is going to be equal to 36, the perimeter of the framing. The perimeter in this case is going to be equal to 1, 2, 3, 4, 5, 6 h's, 6h, plus 1, 2, 3, 4, 5, 6 x's, and then this last little bit of the like semicircle, basically, which is, well, the circumference of a semicircle is 2 pi x, or 2 pi r, but yeah, multiply that by a half. Okay, so again, I'm just going to erase this because it starts to look a bit messy. Okay, cool. So our 36 is going to be equal to 6h plus 6x plus pi x. The 2 and the half cancel. Now we're going to take this 36 that side and the 6 to the other side. Okay, so 6h is equal to 6x plus pi x minus 36. Now we're going to divide everything by 6 on both sides. And what we're left with is our h in terms of x, like stuff. Yeah, x values and whatnot. Okay, minus 6. Cool. So we're going to pop a box around that. And then from there, we are going to pop a box around, well, we're just going to take our area over here. Cool beans. And we're now going to pop our h that we just solved for into that equation. So a is going to be equal to 4. I'm going to put the x here so that it's easier to look at. And then we have our x plus pi x over 6 minus 6. Add that to the half pi x squared. Okay, now we're going to distribute this 4 in to every value inside the bracket, and we're left with 4x squared plus, okay, I can't decide, should I write 4 over 6 or 2 over 3. I'm just going to write 2 over 3. Actually, I won't, because we're going to have to simplify it. Okay, so 4 pi x squared over 6 minus 24x plus a half pi x squared. Okay, so the reason I didn't write this in terms of, as in like 2 over 3, you know, is because I see that here we've got a like term, and so we're going to have to add them together. So when we're adding these two like terms together, we need a common denominator, which in this case, I'm just going to choose it to be 6, because I'm pretty sure, yeah, that's what they used. So 4x squared minus 24x, and now we've got our like terms, which is going to be 4 pi x squared plus, here we're going to multiply by 3 over 3, which will give us 3 pi x squared, all of that over 6. Okay. Cool. Have I done something wrong here? I have done something wrong. So apologies for that. I can see already I've done something wrong. I'm sorry if you guys are shouting at your screens. So when I took this h over, and when I took the 36 over, this 36 obviously got a negative. This h should have got a negative. And so this then would be negative. And so that would make all this stuff negative. So that would be negative. This would be negative, this would be positive. So when you multiply that and that together, it will give you a negative value. Multiply that and that together, again, a negative value. And then multiply that and that together, it gives you a positive value in this case. Okay, I hope that clears things up. Which means that's going to be negative. This 24 is still going to be positive, now. And then this 4 pi r what is going to be negative. Okay, so that's how we end up getting our negative 4x squared plus 24x minus pi x squared over 6. Okay, sorry about that mistake there. But again, if you see that you're making a mistake, go back, look at your calculations. You'll find that for the most part, it's usually a silly mistake. If you've done something like crazy wrong, like you've used the wrong formula for a circle or something, I'm going to tell you to stop doing past papers, go do theory, because if you're going to do past papers and then like use the wrong formulas and, you know, misinterpret graphs and stuff like that, it's not worth it. You need to know your theory. That's why in the introduction video I said I'm basing this all off of the assumption that you guys have done your theory. So yeah, cool. So that's our area, and we can see that it's right. This is technically written there, and you know they swapped, but for the most part it's right. Okay. Then for 1.2, we're asked to determine the length of the base PQ for maximum area of the window. Okay, so the base PQ is what? It's 2x. Okay, so PQ is equal to 2x. Okay, so what are we looking for here? We're not looking for a maximum value of PQ, right? We're not looking for like a maximum value of this 2x. We're specifically looking for the maximum area of the window, okay? And so what we'll find is that we're actually just going to solve for this equation over here. We're going to find the maximum of this. And when we find the maximum of this equation over here, we will end up, sorry, let me just, why are you fighting? Okay, there we go. So when we find a maximum for the area, specifically in this form where we only have x values, okay, we don't have h. If we had h, like in this equation over here that we solved for, the equation that we made, right, you're going to have a problem because you're going to have this h value as well, and you don't know what the value of h is, okay? And specifically, we're working with PQ, which in this case is just 2x. So that just gives you an indication that, hey, you don't need to do all that and get the h value. Okay, so what we're going to do is we are going to optimize. So we're going to let a be f of x. I always just do this because it just makes things a bit easier and a bit more consistent, because you know you'll always be working with an f of x, and that just sort of simplifies things a bit. Okay, then we need to derive it just one time. And the reason I say just one time is because this is a quadratic equation. It does not have like x to the power of 3, it's not cubic. And so to get max values, you'll only need to derive once and make that equal to 0. Okay, so this is going to be 24 minus 8x minus 2 pi over 6x. I hope that's right. Okay, I could be wrong, but I hope that's right. Anyways, so we're just going to keep solving and hope for the best. 0 is equal to 24. Again, I said we're going to make the derivative equal to 0 to optimize, and I'm actually going to write this as 1 over 3 pi x. Okay, so from now we just need to solve for x. Okay, so the way we're going to solve for x is obviously just by solving this thing. Okay, so we're going to have the 24 on one side and make that equal to the 8x plus a third pi x. Okay, so I basically took these to the other side and then left the 24 here and then flipped my two sides. Yeah, I hope that makes sense. Basically, these signs changed. This became negative, but then I took it to the other side. So it became positive 24. Okay, I hope that makes sense. Yeah, cool. So from there, we are going to put this side in terms of x. You always want to isolate your x. That's why I took the 24 over. So 24 is going to be equal to 8 plus a third pi. Okay, so now don't overcomplicate your life. Don't try to simplify it. Just divide the whole side. Divide both sides by this thing. Okay, which is the 8 plus 1 over 3 pi. Okay, I do not actually have my calculator with me right now, so that's fun. Let's see if the calculator does that. Scientific. Does it have pi? Do I see pi in here? Yes, it does. Lovely, 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 lovely. Okay, so we're going to say 24 divided by 8 plus 1 divided by 3, close the bracket, multiplied by pi. And that's going to give us 2.65. Cool. 2.65. So x is equal to 2.65. What? Okay, so the question, to answer the question, it asks for the length of the base PQ that will give a maximum. So PQ, again, we said is equal to 2x. So PQ would then be equal to this. Times that by 2. 5.31. Awesome. Cool. Let me just make sure I round it off properly there. Yeah. Cool. So it would have to be equal to 5.31 units. Some teachers are finicky if you don't put the units, so just put it in there. Oh no, meters, because they gave you meters. So it would have to be meters. Yeah. Again, yeah. Some teachers are just finicky. They'll say it's wrong, even though it's right. Okay, so the length of PQ would have to be 3.5 meters to give a maximum of the area. Okay, so what you can do is you don't need to substitute in values of PQ, but maybe try substitute in a few values of X. Maybe try substitute in 2, substitute in 3, and see what that area gives you. Okay, and then you'll see that certain values of PQ will just give a maximum of the length of the area of the window, basically. Yeah, I don't really know how to say that other than actually solving for it, but I really don't want to do that, so please guys forgive me for that. But if you, for example, have this here, let me low-key just trace this. There we go. Okay, so if you are working with this here, okay, and you still need that semicircle, okay, and you still need that H, all that type of stuff. But if your X is smaller, your H can be bigger, okay, because the area of this window will have to, will increase or decrease, but you're limited by your frame, okay, so you only have 36 meters of framing. So if your X gets smaller, your H gets bigger. If your H gets bigger, your X will have to get smaller to compensate for the H getting bigger. Okay, so essentially, if you make this X really small, you're going to end up with this really long thing. Okay, because your H will be able to be much bigger. Okay, but if you make your X too wide, then you're going to be sitting with a situation like this where your H is really small. Okay, and you obviously don't want that. Okay, so yeah, it's basically just about finding that balance, and then that is your optimized value. And so the way we find that optimized value, the easiest way, is just to find the derivative. Okay, so what you'll notice, okay, and this isn't a very clean-cut example, but you'll notice that this in terms of X, basically this, technically speaking, would be your gradient. Okay, this 8 plus 1 over 3 pi. Okay, so that would technically be your gradient of this line, okay? Of this line, which is linear. You guys can see that that's obviously a linear thing. And I'll actually see if I can plot this and see if it's going to be annoying or not. Okay, so we are going to have y is equal to 24 minus 8x minus 1 over 3 pi x. Okay, so let's see if it will plot. If it won't, I mean, oh well. Did I turn this off? No, I didn't. Okay, so, it's not working. But if you were to put this into Photomath, for example, it would give you a linear graph, and I would assume it's going to be decreasing, okay? But then if you look at the actual first equation of the area before we derived, okay, which is this one over here, okay, you see that it's a quadratic equation. So it being a quadratic equation, okay, I don't know exactly what it would look like. Again, I'm assuming here. But let's say this is your Cartesian plane. And is it increasing, decreasing? I'm pretty sure it's decreasing. I'm pretty sure it's a sad phase. So let's say it's decreasing like that. Okay, so this point over here, basically, and also your x-intercept of the derivative is going to be your maximum. That's going to be your optimized value. And so as soon as you derive a quadratic function, you get this line, okay, which essentially would give you the value of this point and its tangent when it's equal to 0. Yeah, I hope I'm making some sense. yeah, I implore you guys, just put those formulas into like Photomat and you'll see that, yeah, everything will start to make sense.